शावहै Om Shanti Shanti Shanti. Okay. Thank you all for joining on time. Appreciate your promptness. Namaste, Guru Priya Chaitanya ji. I'm Shrikant. I missed you last week because I was traveling. So you can take it away whenever you're ready. You can share your screen and we can get started.
Are you able to see my screen, Ji?
Not yet.
Okay. I think, okay.
Yeah, it came up. Yeah.
Namaste, all. Happy to meet again. In the last session, we had an overview of the Indian Ganita tradition, and we also saw how over 3 eras, that is the Vedic era, and then the Siddhantic era, and the post-Siddhantic era, we can broadly classify into. We did spend an ample amount of time in the Vedic era, and in the post-Siddhantic era, in the Siddhantic era, we did capture a few aspects as well. But in the post-Siddhantic era, we did not capture much, but it will unravel itself in a couple of more sessions. We also saw through a few examples how it was through poetry that all ancient Indian source texts were composed in. And this demanded every single mathematician to not just be a good mathematician, but also to be a literary giant, so to speak, so that they can communicate all the rules, results, theorems, questions, answers, proofs, all that through largely poetry. And we saw how Mula Granthas were there and also Bhasha Granthas were there, wherein Bhasha Granthas largely in prose, some places a mix of poetry as well. And we saw that there is where a lot of commentary is written and a lot of upapattis, the more elaborate discussions, all that is present. Today, we will also look at a very interesting, simple, yet something that we must all rejoice, an aspect of the Indian mathematical tradition. Most think that it is zero, that is Bharat's greatest contribution to mathematics. There is no denying or doubting that, but the fact is it's not just zero, but it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, the entire decimal place value system as we know it today, and the way we operate with numbers, and various other facets of working with numbers, and various Vedic techniques in arithmetics and so on work very well because of the robust design of this decimal number system. We are all still taught tally marks in our educational component. And this was perhaps in the Western construct, one among the earliest historic records of how enumeration was logged into in the um, in times when a sound number system was not really present. There are ample evidences of various cave drawings and so on about how, keeping track of log, people, time, etc., people had used the tally marks. And we all know this system very well. Every fifth uh, count makes the first four noted slashes into a cross. And this kind of number system, is it really robust? If you ask us, see, just to say 18, it takes this much space. If one has to write 1853 in it, it's not a very robust system, right? It takes a lot of time just to write that number, 1853, for instance. When we see the other numeral systems of the other civilizations, we see that they are mostly extensions of the tally marks themselves, with some new symbols added to represent larger values. The Greek, Hebrew, Egyptian numerals were all mostly extensions of these tally marks, in fact. In fact, the Babylonians used the cuneiform script. This is considered to be a very advanced civilization by many, and uh, it's a tablet that they used, a sunlight tablet, which was a clay pellet, for instance, and they used like a dharba grass. Like if you have seen a dharba grass, really, not the one that you probably bought for a ceremony, but if you had really seen it grow, next class might be I'll bring what's there in the ashram, and you will see that the reeds that get formed, the thicker grasses, if you cut them, there is a small shape to them, right? And if you take that grass and then on a wet clay tablet, if you were to poke a hole, it will create a certain impression, and that impression would look something like this. It will look like this based on the grass reed, right? So the Babylonians used such thick grasses that were a particular kind of grass that they had on their water banks, and they used this grass to sort of make insertions and then talk of numbers. Okay, in the Babylonian system, this is one, and if I have to write, I'll make two insertions like this. Two. This will be three, and this will be four. This will be five, and this will be six, seven. It goes on like that. Eight and nine. Once you have done nine, then what they do is they turn and then make a press like this, right? Making horizontal ones as tens. And then if they shift a place, it works like this. So there is one here and then two tens, right? And then straight three ones if they are right, then that makes a 60 each. Again, whenever the number becomes 60, it will turn straight back again. So it was not really easy to really understand this. However, they needed a sexagesimal number system mainly because some among the earliest approximations of a year were 360. That's why even now in a circle we have 360 degrees. Mainly this comes from an astronomical standpoint, where we understood that every year is in fact approximated to 360 days earlier. So thereby cyclical things gotten these 360 divisions made, and thereby a degree was understood. Basically a 360 division of the entire circle, and the 360 and the base 60 for it to come in itself, astronomical origins are there. So this worked like this in fact there are many inscriptions like this, where the population of a ram, the population of sheep, they're all that have been recorded very well. And then the Egyptians, see, they had a number system like this. These are called hieroglyphs, where certain symbols take note of different place values, say 1, 10, 100,000 and so on. And then for instance, to just express 47,209, half your wall will go away by the time they finish inscribing and drawing this, right? So there is a sort of a a diagram like this, where this with three tongs become 300, with four tongs they become 4,000, this becomes 3,000, and so on. So this was, they started creating these hieroglyphs. None of these systems are robust. And if you see the Mayan, Egyptian, Hebrew, Greek numbers, they're all extensions of these marks, right? Just the way how a tally mark would work. But we see that when a place shifts, what they try to write the symbol, and that inspiration seems to have been in the Babylonian tradition as well. We all still study the Roman number system. Just to write 1988, right? There is MCMLXXXXVIII, right? And then doing that and doing multiplication with Roman numbers, I encourage you to sometime Google up and then see how elaborate and detailed and time consuming it is to even do multiplication with Roman number system. And as I was commenting in the previous class as well, the Romans, they basically employed some people called the calculators themselves, right? That they had to sit and then do. It was not a easy thing for them to. It was not, math was not accessible to, so to speak. Whereas we see in the Rig Veda, earlier than 2000 BC, at least, as I was saying, dating the Vedas, especially dating in an oral tradition, is very, very, very tough. However, different people have different dates, and it goes all the way back, to the tune of even 27,000 years ago, right? So there are different dating schools of thoughts, but we can at least safely say even the most skeptical schools rated at 2000 BC. So at least 4,000 years ago, we have had, where we have had a mantra which has clearly the decimal place value names in them. त्रीणि सहस्राण्यग्निं त्रिंशच्च देवा नवचासपर्यन्. The Rig Veda says, where we see that we see Trini here, which is three Sahasrani we see here, then Trini Shata, Trimshat, then Nava we see. So Sahasrani, 3 Sahasrani makes that 3,000. Trini Shata makes it 300. Trimshat is 30. And Nava is 9. And so this kind of a place value name we see in the Rig Veda. We were predominantly an oral tradition. However, we see that Karoshthi and the Brahmi inscriptions were prevalent during the 250 CE. These scripts seem to have numeral representations in them. Today, the Devanagari script that we see, which are widely prevalent now, were developed from the Brahmi numerals. We do not know when the Nagari numerals were exactly formulated, very historically speaking. So from the Brahmi numerals, this kind of inscription started coming in Devanagari. That got translated into into Arabic, and from there into the medieval script and then the modern script. All of Europe was still submerged in Roman number usage till the 14th century. The very fact that the decimal place value system reached them, it liberated many of them to do further calculations very easily. You may read all about this. In fact, there is a beautiful book by George Ifra called um, it's called the Universal History of Numbers. It's a fantastic book by George Ifra. He was a primary school teacher in the US. When a question asked by the student that as to how did the origin of all this number system come to be, he did a thorough study. In fact, he took a sabbatical 2.5 years, traveled the world, and he did a thorough study of every civilization's genesis of number system, and he clearly articulates how it all started here. The current usage of number system starts from Bharat. Now it is Even a couple of decades ago, it was called the Indo-Arabic number system. Now it's recognized by many scholars as the Indian place value system, right? It's well known, evidences are there that it was adapted by the Arabs in the 9th century CE. From there, it spread to African countries and European countries. So this very way, right? Every position is, a power of 10, right? This very way, the very way we have conceived this number system belongs to Bharat. We all know this already quite well. So Aryabhatiya, in the Aryabhatiya, we find a verse. It's Aryabhata, he says, he defines how this decimal place value system goes. He says, एकञ्च दश च शतं च सहस्रम् अयुतनियुते तथा प्रयुतं कोट्यर्बुदं च वृन्दं स्थानात् स्थानं दशगुणं स्यात्. So sthanat sthanam dashagunam syat. He says from one place to the other, right? When you shift from one position to other, if there are three digits, the place value shift is a multiple of 10. He says sthanat sthanam, from one position to the another, it's a multiple of 10. Dasha gunam syat. He says this is dasha gunam. So here popularly we study till a billion in the primary education. So the same he gives in the Indian place value names. Ekam, Dasha, Shatam, Sahasram, Ayutam, Niyutam, Prayutam, Kotihi, Arbudam, Vrindam. Right? He gives up to 10 power 9. Of course, were there more place values? Certainly more than that. Many were there. This is just a small summary example of a list of place values given by Aryabhatta. So this, is the list. We must become good at this. Certainly, if we want to become good in Bharatiya mathematics, when I ask you a question like Navani Kharvam, you should be able to say what is that number. Navani Yutam, if I say, you must be able to visualize it as 9 lakhs. Then when I say Kotihi times Sahasram, you must know what that is, and so on. Right? So Leelavati, Bhaskaracharya expands this number system up to 10 power 17. So in fact, Siddhartha, if you didn't know, in a Swayamvara, was asked place values as one among the questions. Siddhartha, who later became the Buddha, in his Swayamvara was asked mathematical questions wherein he was able to even say 10 power 54, 55, 56, which the questioner himself didn't know the place value names for them, and so on, is what records say. We see in Ramayana also 10 power 100 and such numbers being captured. So here we have 10 power 17. Why is this enlisted? Because he's going to give you numbers and sums based on some among these place values. So at the beginning of the text in itself, Bhaskaracharya enlists this. In fact, in the 10th and 12th verses. Ye kadasha shata sahasra yutalakshya prayuda kotayah kramashah arbudam abjam kharvani kharva mahapadma shankavastasmat जलधिश्चान्त्यं मध्यम परार्धमिति दशगुणोत्तरा संज्ञाः संख्याया स्थानानां व्यवहारार्थं कृताः पूर्वैः. He clearly says that these are not terminologies that I am introducing, but purvaihi kritaha. It has been done by our ancestors. It has been developed by our ancestors, used by our ancestors for the purpose of Vyavaharika, for the purpose of all enumeration and transactional knowledge. These number places, Sankhya Sthanana, the names of these number places, has been, these are the samnyas, these are the technical terms for all the place values. What are those? Eka, Dasha, Shata, Sahasra, Ayuta. For Niyuta, he uses Laksha, right? Then Prayuta, Koti, Kramashaha in the order. Arbudam, Abjam, Kharvam, Nikharvam, Mahapadmam, Shankuhu. Then Tasmat, Shankuhu, Tasmat becomes Shankavasta. Tasmat. Shankavaha, this is the compound word, and then Tasmat. Jaladihi cha antyam madhyam parardham, or up to parardham, yes said. In fact, the Vedas also have parardham, but in the Vedic knowledge, parardham, in the context of that text means something else. And in the context over time, parardham has come to mean 10 power 17. Sorry, this is my merger of a few. So far, is this okay for all? Okay. So, having known these place systems, we understand that clearly we were very comfortable having given place values to a very high order. We have been quite comfortable in handling these number systems. Now, let us go to understanding how these numbers got to be represented in the form of a composition. When we already saw that all of mathematics was written in beautiful poetic compositions, right? And if one were to fit a meter and write songs in this meter, then it becomes quite challenging to write numbers, right? So they had to develop ingenious way of representing numbers so that it's very convenient for poets to include numbers in them. So formally, we see three popular number representation systems in Bharat, which are Katapayadi number system, Bhuta Sankhya number system, and the Aryabhatan number system. Let us see them one by one. So when we look at the Katapayadi number system, as the name in itself suggests, it has a certain encoding, and we will see how that this the encoding works. I mean, some of you may have known Katapayadi number system well as well, but let's also see some applications of how it could have been used. And as I was already saying, all this being orally transmitted, the acharyas had to be experts in poetry, and so they had, and they had to weave in numbers within their poetry, thereby creating the demand for such number representation systems. Right? How will they write numbers in poetry? That's the question. Right? One such system is the Katapayadi number system. So we know that the alphabetical system in Sanskritam is broadly divided into swaras and vyanjanas. Swaras mean the vowels, and vyanjanas means the consonants. When we look at the swaras, we see I, u, r, l, a, I, o, au. We study them like that, but in the traditional listing, it's a, o, I, au. That's how we be it in Paninian. Some among the traditional listings of the number of the alpha of the vowels. Today we study as A, I, O, O, but actually A, O, I, O was the traditional listing. Then we know the Ka Varga, Cha Varga, Ta Varga, Tha Varga, Pa Varga. And we see that all these five, this is a 5x5 grid. This is important to know. The other 8 is does not fit into a 5x5 grid. So different people utilize this these properties and then exploit these properties to create intelligent number systems. Okay, when it comes to Katapayadi, we broadly know first we must know that the Sanskrit alphabets are classified as swaras and vyanjanas. Swaras are vowels and vyanjanas are consonants. Now we all know that the sounds that we produce are a combination of these consonants and vowels, right? We all know these, be it through our own respective mother tongues or any of the vernacular languages in Bharat, or if you know a bit of Sanskrit or Hindi, you all know that a mix of these consonants and vowels, they make these formulations of letter combinations. In fact, letters like A, E, I, O, U in the English vowel system, right? It's really tough for Indian children here in Bharat to easily pick up which is a sound that starts with a vowel and so on. And so at ashram, our Gurukulam children always think of the words in English in Devanagari and then see if unique for an if in front of the word unique a should come or an should come the article they sort of transliterate it into Sanskritam and see if the first shabda is a vowel or a consonant shabda, thereby quite easily classifying the sounds. So two consonants can also combine to give conjunct consonants in Sanskritam. Ik plus ta will give kta. In Shakti, we see ik, right? And then ik plus sha, the Shanmuga sha, will have ksha, right? Similarly, it plus ra, stra, right? Kha, kha, ga, ga, nga. That nga plus ja, j plus nga makes it nya, right? So these are all some among the conjunct consonants. So these are all the foundational things that we should know about the Sanskrit alphabet in itself to appreciate and understand the underlying logic behind the Katapayadi number system. In the Katapayadi number system, as the name itself suggests, Katapaya Adi means Katapaya, take the values 1. Okay. This is the rule in the Katapayadi number system. Katapaya, take the values 1. The vowels, when they stand alone, they represent the number 0. The same vowels in conjunction with the consonants have no numerical significance whatsoever. So the 33 consonants, k, k, g, g, all these are associated with a numerical value. How does it work? It works like this, right? K, t, p, y. All these take the value 1. And sequentially 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So this nya will have 0, tha tha da da na tha tha dha dha na will have the value 0. Pa pha bha ba ma ends here, yara lava shasha saha ends here. Later, because of the Kerala school, this l came into existence as well. All the standalone vowels, they take the value 0. So far clear for everyone? Any doubts here? So far you are able to follow? You must be able to visualize this table whenever I ask you to solve a few problems, later. So it's good to get accustomed with it, or just to get an understanding of our participants here. Would all of you know some basics in Sanskritam, or all of you are convenient, or are you all comfortable with this, with the letter system that we have here in front of us? Okay. Okay. I see a lot of thumbs up. Great. Okay. Great.
That la has always been there, right? Even in the Vedas. Agnimile, Purohitam, la is not new. I mean, you said it is from Kerala school.
Okay. In the Katapayadi usage, they have never used this number system unless and until the Kerala School of Mathematics started employing them.
Okay, usage. Okay. The Katapayadi usage. Yeah.
This is given by Shankara Varman in the Sadharatna Mala. He says, so it's the Indian tradition, right? No matter what the concept is, we've got to write a poem out of it, right? We've got to encode this in a verse, right? So this we should get comfortable with. No matter what concept that we are going to discuss, they are all available in the poetic form. Nanyavachascha shunyani sankhya katapayadayah mishre tupantya hal sankhya nacha chintyo halaswaraha, says Shankara Varman. Shankara Varman tries to beautifully capture. Of course, there are different, things that capture what Katapayadi is. This is a simple verse that we can easily learn and easily teach children as well. So it's a very friendly verse from Shankara Varman. Na and nya and ach. If all of you know what is ach in Sanskritam, based on the Maheshwara Sutrani, ach stands for, what would ach stand for?
Swaras.
Yes.
Swaras.
All the swaras. Yes. All, I don't know if all know this here, but the legend has it that Panini was a Mandabuddhi student. I mean, in fact, he was the son of a great scholar himself. However, it seems that he could not easily be admitted into any of the Gurukulas, and his father was so disappointed in him that he was given, sort of, he was given eviction notice from every single gurukula that he went to, and his father didn't know, the great scholar that he was, could not manage, that he had such a mandabuddhi person. And those days, the entire society was organized into not just rural urban, but it was nagara, grama, and aranya. This classification of the societal structure, Bhishma also talks about in the Bhishma Parva, and he says how Raja's, uh, you know, dharma is to ensure that these three ecosystems survive independently, and he further classifies Aranya into Shrivana, Mahavana, and Tapovana, and how it is. I'm taking a small digression here, but very interesting to know, however, that beautiful understanding of, because I've often heard children and many people debating and understanding uh, this conundrum of, was hunting dharma or adharma, was is hunting something that was allowed or not allowed. You see, the structure of the vanas earlier, the aranyas, were threefold, as Bhishma says. They are the Shrivana, Mahavana, and Tapovana, where Shrivana is forest agriculture. It's just it's vana for Shri, for wealth, to create timber, to have latex, to create various honey, for many forestry products. They had to maintain certain vanas. They were called Shri vanas. And then came the Mahavanas. The Mahavanas are the current kind of forests, which are reserve forests, right? They're fully reserved for wild animals, where no, except for remote tribal community, as such, you cannot go buy land, register land. You can't do anything there in these reserved lands, right? It was Mahavana earlier. Then came Tapovana, where it was, populated by human beings, be it Gurukulas, be it people in the Vanaprastha, and the life there is more challenging than in a grama, because grama was your industry, nagara was your consumer, and aranya was where it was mainly for austerity, right? The tapovanas were mainly for austerity. There it is the raja's dharma to keep a check on the animal population, and thereby it was the raja's dharma to go there and then hunt and keep this animal population in check. So, like that, Panini's father, it is said, the law, no, it's a legend. We don't have a source text for this, but legend says that he left him in an aranya, and he could not bear him to be, part of the society anymore. There, there he sees a group of rishis who are doing tapasya, who are doing upasana towards Bhagavan Shiva. There, Bhagavan Shiva comes and then helps, um, you know, um, does not help per se. He gives darshan to the rishis there. And these rishis, right, when are given the blessings by Shiva himself, apparently there were 14 rishis, and when they asked for different boons from Shiva, the Mandabuddhi that Panini was, who was witnessing all this, doesn't know what is happening, around him. He's just witnessing all that. It is said that Bhagwan Shiva, in blessing them, played the dhamaru each time he blessed each of these rishis. And that dhamaru nadam, it is said that it was heard by Panini in the form of the Maheshwara Sutrani. Aivun rulruk evong ayauch hayavarat lan yamangananam jhabain ghadadash ghadadash khapa chatata chata thau khapa shasha sir hal, like that. He heard all this, this that, the way he played dhamaru, it sounded like these aksharas, and that the Maheshwara Sutrani is the bedrock of the entire Paninian grammar, where there is a terminating letter called the ith letter in the, and wherever you would like to borrow a terminating letter, there the sequence terminates and the rules are written as per the sequence. So in that, I un rulruk e wong I ouch, make ach together if you want to truncate that. What a brilliant way to organize letters, and how do you, sort of contract them. Because sutras, alpaksharam asandigdham saravat vishwatomukam. So you've got to write sutras, and there is a certain way to write them. You've got to concisely write things, and you've got to arrive at beautiful notations within that, and how you want to present various aspects. So in the sutra rupas, when texts are presented, it has its own charm. Padya rupas has its own charm. And in the Sutra Rupa, we know very clearly that Ach means all the vowels. Hal means all the consonants. So here we see that Na, Nyau, so Nanyau becomes Na, Cha, Nya, Cha. So Nanyau and Ach, right? Achascha, Achaha, Cha. It becomes Nanyavachascha, Sunyani. So the Na, Nya and all the vowels denote zero. Sankyaha Katapayadeha. The numbers begin from Katapaya. Right. That's what he says. So in a conjunct consonant, Mishre right? Upantya Hal Sankhya. So in a case of a conjunct consonant, right, one must take the last consonant, right? Which that alone will denote the number. What does he mean by that? We will come to it. Nacha chintyo halaswaraha. Whenever there is a hal without a swara, aswaraha, don't have to worry about it. Okay. What it means, we will see in a moment. Okay. We will first try to take simple examples and understand. So, gu is made of ig plus u. Right? We are not bothered about any of the vowel that is attached. So, gu would mean the number 3 in Sanskrit. Because why? This kha, kha, ga. Ga is 3, right? So gu would stand for 3. Ankana vamato gatihi. There is one more rule when it comes to decoding numbers. When a whole word is said, you've got to convert each of these consonants into a numerical value and then reverse them and read them. Okay, we'll see some examples. Okay, chataka. If I say chataka, right, what would ch, the value of ch be? We see here, right? Ch takes the value
6.
6. So we write 6 here. And t takes the value 1. And k, beat ka, ki, ku, ke, kai, whatever vowel is attached to ik, it will take the value 1. And then the rule is ankanam vamato gatihi. So the value held by the word chataka is 1, 1, 6. So this is how in Katapayadi number system. So now what happens? So you can take meaningful words, right, and then turn them into numbers. Meaningful words are easy for you to memorize. So you can, in fact, memorize the entire, table for the sign value table, be it, so many data points that you want to. If you want to know the true longitude of moon on all the 354 days of a lunar year, that is presented in the Katapayadi number values. I see some hands are up. Let me just complete these 3 examples, and that way, and then let me engage you. Okay. Sorry. Yes. So now, let's look at will take the value 0. Any standalone vowel will take the value 0. Im, a vowel without a consonant without a vowel attached to it is to be not considered. So im is dropped. It's not even processed in Katapayadi number system. B takes the value 3 here. P, P, B. So 3. And then the rule says Ankanam Vamato Gatihi. You've got to read it in this reverse direction. So Amba takes the value 30. One more example, and then we'll go into questions. Yara la va. Va would take the value 4. Vikramaha. Ik. There is kra. In kra, what you should take? You should only take the antyahal, which is basically ik. The underlying rule is this. Ik doesn't have any vowel attached to it. So drop ik. Right? And whereas ra is attached to a vowel which is a, right? So in vikra, in kra, it's made of ik plus ra. Ik, drop it and take the value of R, which will be 2. So take 2 here. And Ma takes the value 5. Maha, this aha, all of them are upa swara, so you do not worry about them. So Ankana Mamato Gatihi 5 to 4 is the value of Vikramaha. So this is how the Katapayadi number system works. Yes, now I'm open to questions.
Why is the reverse? I forgot to understand.
So it's a convention, right? It's the way it's been used. They have agreed upon this usage as a convention. I don't know what else to say, why it should have arrived at this. We do not know, but it has been a convention for a long time. In fact, what is forward and what is reverse? Both are conventions only. So, yeah.
Probably it helps the decimal notation, like, ekadasha, dwadasha. So you are coming from the vamato, from the right to left.
That is a good guess, Sriniji. In fact, the way we write, right, in the Sanskrit letters, right? So if I have to say 76 in Sanskritam, how would I say?
Shat Saptatihi.
There I'm saying my units place first, and then I'm telling my tens place. Right? If I have to say 176 or 276, how may I say?
षट् सप्तति uttara, but from the 100 you're coming from the left itself.
So these are conventions, right? So what came, how these, came into being, we do not know what rational, but this sort of conventions came to be, just to illustrate that.
But
Mahodaya,
Ashtottara Shata will still follow the same convention that you are talking about. Sankhyanam Vamatavadi.
Yes. So, true.
so
Somebody
Mahodaya,
else.
so I had a question. So
Mm.
this can be convention, Mahodaya, like driving on the left side of the road, right side of the road, right? But so we know that, for example, today we follow left to right, and Arabic systems, for example, to right to left. And I've read elsewhere that in Indus Valley, both kind of things was tried, right? Do we know when either of these were they ever standardized or were they just region dependent? How uniform or different were the conventions throughout India and throughout time, at least mathematically?
With written script, G, it is really tough to say, because in the kind of plundering that has happened in Bharat, the kind of dating challenges that we have is only because of the large libraries that have gone. And there's a lot of historic context to it. But I'm really a very small person to comment on any of this. But yes, but Ankana Mamato Gatihi, that convention has been there in Katapayadi, it has been there in Bhuta Sankhya as well. It could mean for a few things. It could also be because what I'm saying might not be true. I'm just wildly guessing here. But a lot of, a lot of padas, they begin with a vowel, right? If you begin with a vowel, and that turns into the last digit of 0, right? That gives certain freedom for some people to choose words and so on. But it would not apply at all in the case of a Bhuta Sankhya. So I'm really not sure as to why this convention started or what purpose it serves per se. But people have used this convention quite a bit extensively, and they are very convenient in it. But what this makes for is a wonderful exercise for children. So I start saying words, you can just process that in your mind and turn that into numbers. It's a beautiful neuroplasticity exercise for children. They're reflecting the word, but they're compiling the shabdas, as I'm saying, and they're reversing it in their mind. It's a very beautiful experience. In fact, if we are going to go down this road, and we're going to see how this has been used in the Melakarta ragas and so on. But this is a beautiful encoding system. Is this okay? Can I leave this discussion here, and shall I?
Yeah. Thank you, Mahodaya. I'll follow up with you offline. I have
Sure.
just certain speculations, but
Yeah, please, please, please. Yes.
My question, follow up on this one before we leave the subject, is should we even think in terms of civilizations here and language, um, or should we think like pre-civilizations here?
Okay, that puts us in a different spot altogether. Um, so we know that Sanskritam is Deva Bhasha, it's Apaurishaya, it's pre-anthropogenic in its nature, and so on. But where is the proof for it? What's the discussion around it? We do not know. Shraddha wants, they take it up in a particular way. And so if you go back to Sanskrit itself as a language, and then this now the kind of Katapayadi system that we are talking about relies on this kind of an the Nagari script. So when do we conjecture this came or that came, we do not know. However, this was not the earliest number system that was in use. Later, and the next class will be looking at Chandas Shastra and the combinatorial math in the Chandas Shastra, where you will see that actually the earliest usage of such number system in sutras or in padyas actually is the Bhuta Sankhya number system. That predates Katapayadi number system is one postulation that many scholars could agree with. But the background of what Katapayadi number system is, you will see a lot of papers out there, a lot of people trying to postulate. But many of these speculations as to what could have happened historically, history is not at all my domain. I definitely savor it. I definitely respect it. But it largely puts us in so many inconvenient places and also on a defensive stance at every point in time to try and say, hey, so this is predates that and that predates this, thereby this. However, we this group especially, we can be sure of of some among the wonderful achievements of the ancient Indian thinkers, and banking on that we can just go on enjoying some among these principles and some among these mathematical thought processes that the civilization offers, which also has a huge pedagogical usage, as I was speaking of in the previous session. Is that okay, Ji? Okay. So this is your homework for the day. You can screenshot this or how you would like to do. Shastram. So be very clear, wherever, whichever shabda in Shastram, there are two, hal shabdas without a swara, right? Is and it. Only ra has a shabda, im shouldn't have a shabda. Right? These are solutions. We'll discuss this later. So this Katapayadi number system was ingeniously used by various poets and in various contexts. Okay. So the story of Melpattur Narayana Bhattatri. Narayana Bhattatri is the author of Narayaniyam. Right? In fact, he is the Sishya of Achyuta Pisharati, one among the greatest astronomy mathematician, astronomer slash mathematician in the Kerala School of Astronomy tradition. He studied under him, we know. However, we also know Narayaniyam was the legend of Narayaniyam goes that Narayana Bhattatri, is was certainly, the legend has it that his guru, we do not know if it was Achyuta Pisharati. However, he studied under him, but the Narayana Bhattatri's guru seems to have had a great disease. He seemed to have prayed so intensely and got the disease transferred onto himself. And then he went to Guruvayur, where he composed the Narayaniyam, which is the Srimad Bhagavata Sangraha, basically it is. But we know very clearly Narayana Bhattatri is a very astute mathematician and astronomer. For example, the birth of Bhagwan Shri Krishna, he talks about the angular separation between the sun and moon. For example, in the Krishna Ashtami, right, he says that when the moon was reaching the zenith, Bhagavan Shri Krishna was born, right? Instead of saying what tithi he was born in, etc. Right? So we know that he's a good mathematician, astronomer. He closes this devotional poem Narayaniyam with a chronogram, with this expression that Ayur Arogya Saukhyam, he says. We all know Ayur means longevity, health means, Arogya means health, and Saukya is happiness. On the other hand, this very phrase that he utilizes is a chronogram. Many people use Katapayadi for even chronogram. If you convert this Ayur Arogya Saukhyam into the Katapayadi place value systems, and if you reverse the numbers, you will get 171210, which is the Kalyahar Gana. It is the Kalyahar Gana. In the Indian Panchanga systems, there's something called Kalyahar Gana. As per the post-Siddhantic astronomical traditions, such as Aryabhatta and so on, we look at dating Kali, the birth of Kali, as around either February 17 or 18, 3102 BCE, right? That's how the astronomer, post-Siddhanta astronomical traditions date. Of course, right now, so many debates, so many understandings about Mahabharata timing, Ramayana timing, thereby Kali Yuga time, all that is always happening. However, the Yuga in the astronomical system means something else. In the course of our discussions later, we will see some astronomical gems and try to understand the mathematical reasoning and the scientific reasoning behind the Kalyahargana itself. So here, however, he says this is the number, this is the date. He's just signing off with the date on which he had composed this poem, completed this poem. If you convert this into Kalyahargana, it dates back to 8 December 1586 CE, this chronogram. We see that this tradition has been there very much in the Kerala school. So, for example, this is the Tantra Sangraha written by Nilakanta Somyaji in 1500 CE. He begins his entire work with a chronogram and a Mangalacharana. He Vishnu Nihitam Kritsnam Jagat Tvayeva Karane Jyotisham Jyotishe Tasmai Namo Narayanayate. He begins like that, wherein the first pada of this Anushtup Chandas, the first 8 syllables put together, they are a chronogram. Similarly, he finishes the entire work with Lakshmi Isha Nihita Dhyanaihi. So he meditates upon the Isha of Lakshmi and then he completes this work. Both the commencement and the completion of the work are given in the first pada of the first verse and the third pada of the last verse. The dates are given as chronograms. So if you convert Hey Vishnu Nitam Kritsnam, you will get the Kalyahargana date as 1680548. Similarly, this corresponds to the date of March 22, 1500 CE. Similarly, if you see the closing, the completion date, it corresponds to March 27, 1500 CE. Looks like this phenomenal work with 472 verses. Very, very intricate work, right? Seem to have happened only in 5 days. Yes, started and completed this composition in 5 days. So, this is one usage. Of course, I have not brought in sine table here when we discuss trigonometry in the final module of mathematics. We will see a bit of how this is used extensively. Katapayadi number system has been used extensively in trigonometry. Another very interesting application for the Katapayadi number system is the Melakarta ragas. So the Carnatic music system has the traditional 72 Melakarta ragas. All ragas other than these 72 are called Janya ragas. Right? They are a modification of these Melakarta ragas. Out of these 72 Melakarta ragas, these are an ordinal list. Okay, the 72 Melakarta ragas are a combinatorial ordinal list. And if you look at that number of the ordinal number of a Melakarta raga, you will be able to decode the entire raga, the Arohanam, Avarohanam of an entire raga. The thing about the Melakarta raga is that it has all the swaras in the, there's one form of the swaras available in all the Melakarta ragas. So given a raga name, you will be able to decode the entire, given the raga's ordinal number, you will be able to decode the entire raga. That's how mathematically the raga system has been beautifully, made. So we will see that with an example. But let's say you know the raga name. The first 2 syllables of the raga name, if you turn them using the Katapayadi values, will give you the raga rank. Right? That's how they have created these 72 ragas. So the first 2 syllables will turn into the ordinal rank of that raga. And if that rank of the raga is less than 36, it is Shuddha Madhyama. If it is greater than 36, then it is Prati Madhyama. That is Ma 1 or Ma 2. Right? That gets fixed based on if it is less than 36 or greater than 36. Then, based on that, the next step, it involves, if it is greater than 36, subtract 36 from it, you will get some n, right? If it is less than 36, keep it as it is. Then take that n and reduce that by 1. Okay, this revised Melakarta number -1. Let's take this value n. And if you divide that n by 6, the quotient and the remainder that you would get. If you divide any number by 6, the possible quotients and the remainders are, the remainders we know can only be 0, 1, 2, 3, 4, 5, right? Can be the only remainders. Now that we have truncated the n, if it was greater than 36, we reduce 36 from it, right? So we have always truncated n to 36 right now, right? So the quotient also can only take the value 0, 1, 2, 3, 4, 5. Because 36 minus 1, even the 72nd raga, if I reduce 36 from it, will be 36. If I do -1 to it, it will be 35. Right? So thereby, if I divide it by 6, also the quotients that I can get are 0, 1, 2, 3, 4, 5, 6 only. Okay. So with this in itself, you can sort of delineate the entire raga. If the quotient is 0, it is Re1 Ga1. The quotient is 1, it is Re1 Ga2. If it is 2, Re1 Ga3. So Re1, 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 Ga1, Ga2, Ga3. Right? Then comes Re2, Ga2, Re2, Ga3. Okay. Re2 Ga1 will never come. Why? Because Re2 is Ga1. And so it's, let's musical people might understand this better. I mean, like it's these are in between notes, right? You can't transition from Re2 to Ga1 ever. So Re2 Ga2, Re2 Ga3, then Re3 Ga3. These are all the only possibilities, right? Re1 with Ga1, Ga2, Ga3, then Re2 with Ga2, Re2 with Ga3, then Re3 with Ga3. Similarly, the remainder will say Dani. The 1, Ni 1, the 1, Ni 2, the 1, Ni 3 for 0, 1, 2, 3. The 2, Ni 2, the 2, Ni 3, and the 3, Ni 3. So thereby, for example, if we take Dhira Shankarabharanam as one among the examples, Dhi, the stands for 9. Why? Ka, ta, right? Ta, ta, da, da, na, ka, ta, da, dha. The dha stands for 9. Right? And ya, ra. Ya is 1. Next letter is ra. Ra stands for 2. Ankanam Vamadogati. If you reverse them, you will get 29. So the rank of Dhira Shankarabharanam in this ordinal list is 29, therefore. If it is 29, we all know it is Shuddha Madhyama, which is Ma 1. Right? So Sa, Pa, Sa are fixed. And now Ma 1 is already fixed. Right? Now, if you take 29, if you reduce it by 1, you get 28. Right? And if you get 28, 28 divided by 6 will give you the quotient as 4 and remainder as 4. So if you go to quotient as 4, it is Re2 Ga3, and remainder as 4, it is the2 Ni3. And thereby, we have the entire raga. So the real exercise for children, especially our children who are musically learned and our children who you are teaching Sanskrit to, this is a brilliant exercise to do. Okay, this really flips their mind. And so you can name the raga and you can ask them to convert the first 2 syllables into Katapayadi, reverse it, and then so this processing time ideally it should take you no more time. With over practice, say the raga name and you'll be able to just do the Arohanam, Avarohanam. One more example is Raga Senavati. Sa is 7, Na is 0, so 0, 7. So it is less than 32, again Shuddha Madhyama. And 7 reduce it by 1, which will become 6. 6 divided by 6. It gives you remainder as 0 and quotient as 1. Right? So Re1 Ga2 for 1 and the 1 Ni1 for 0 as a reminder. And this is how the Kattapayadi number system works in the Melakarta ragas. There was a question by someone.
No, not a question. This is amazing. I mean, we already have a topic for the presentation end of the module. We'll just take a bunch of ragas and then we can figure this out.
Yes, certainly.
Very beautiful.
So this, you see how it is structured, right? So this is the cyclical construct. So this will repeat. This is divided into two such cuts. In fact, in Chidambaram, one among my co-researchers' great-grandfather he has this, sort of drawn in old Tamil in a very large sheet. In fact, he has done charts like this for Tala Prastara, Thana Prastara, and so many other things as well. Okay, anyway, so this is a cyclical ordering, right? So when you get 1, 2, 3, 4, 5, 6, right? In the first segment, you've got 1, 2, 3, 4, 5, 6 further. So this 36 divisions, right? And this is the underlying cyclical representation. So you will see the one, ni one, the one, ni two, the one, ni three, the one, ni two here, right? This entire thing is a combination of re one, ga one for the quotient of one, all the possible reminders. Like that, it goes on, right? So this entire cycle goes on. Of course, in the 72 ragas might be a very good presentation that you can do. Is there are some exceptional ragas where this rule won't apply. However, you can see that if you slightly, read the raga name very carefully, you will see that might be in the next two syllables it will be there, and things like that. There are the one or very handful of exceptions in the raga names. You just have to, because they probably wanted to make a good name for it, look at the bhava of the raga, look at which deity it might correspond to, all that, and still, so that's all I was thinking when Kiravani ji was, receiving prizes, receiving the. I was only thinking of Katapayadi number that day when he was receiving the Oscars. So Kiravani and all these things, you please do try all these 72 ragas on your own. And this very, very beautiful system that they have developed, and the kind of combinatorics and the innate mathematical sense. If you look at Sangeeta Ratnakara, the last chapter is fully mathematics. People who study the Sangeeta Ratnakara sadly are not studying the last chapter. Very rigorous mathematical chapter it is. So summary of Katapayadi number system: standalone vowels represent 0. In conjunction with consonants, we don't have to worry about them. The 33 consonants have the numbers assigned to them, 1 to 0. The special rule to consider is whenever consonants are in conjunction, take the consonant that is attached to the vowel alone, right? And hence, we see various applications of Katapayadi. A few of them we have seen. Mind-blowing trigonometrical applications are all yet to come. So now we will look at the Aryabhata number system. I'm just rushing slightly here. Pause me anytime if it is too quick for you. No, Aryabhata, the genius that he is, he wants to do a lot more things, right? In a single syllable, he wants to represent numbers to the magnitude of 10 power 16 because he's an astronomer and he wants to only write big numbers and big data, right? So, this is very, very difficult to pronounce this Aryabhata number system, right? Extremely convenient to write. In a very short, you can write a huge, number system. Okay, how does this work? This is slightly different from the rest of the Katapayadi number system. This is based on Swara Vyanjana, classification. He calls, this Swara and Vyanjana, he'll be utilizing it quite, in a unique way. As I said, the traditional way is A, I, U, R, L, E, O, I, O. A, E, both are having the same value. So he uses the vowels. Vowels decide the place value. Okay. So in the Aryabhata number system, the vowels decide the place value. In the Katapayadi number system, the vowels have no role, right? When they are in conjunction with a consonant, right? So in the Aryabhata number system, so in the Katapayadi, Ka, Ki, Ku, Ke will have same value. But in the Aryabhata number system, Ka will have a different value. It will be to the magnitude of 10 power 0. Into 10 power 0 means units place. Ki will be curse value into 10 power 2. Ku will be curse value into 10 power 4. R will be kr means curse value into 10 power 6. Right? So the longer vowels take the same place as their shorter vowels. So the place value is decided by the vowels themselves. Now, as I said, the consonants, right? There is a 5x5 grid possible. And then there are 8 things that do not fit the 5x5 grid. These are called Vargiya Vyanjanas. And these are called Avargiya Vyanjanas. So, Varga also means a square, right? So, they form a proper 5x5 square matrix. Avargiya Vyanjanas, they cannot fit into this matrix. So, Vargiya Vyanjanas have sequential numerical values. Avargiya Vyanjanas have a skip count number values. So Vargiya Vyanjanas, Ka to Ma, will sequentially have the value from 1 to 25. Right? Ka to Ma will have sequential values 1 to 25. So very easily, if you remember the Varga that they belong to, you will know which multiple of 5 you should add to it, right? Cha Varga, Ka Varga, after that comes Cha Varga, right? So it will be, Cha is the first letter in that Varga, Ja is the third letter in the Varga, which is 5 plus 3 will make it 8. So that's basically a pedagogical tool what I'm sharing here is. So when I say the, you know that it is in the Ta Varga, which is the fourth Varga, right? So which means already 5 plus 5 plus 5 is over. And in the fourth Varga, it has the fourth place. So 15 plus 4, it will be 19. So you can see that this sequential values are there for Vargiya Vyanjanas. For Avargiya Vyanjanas, Yara, Lava, Shasha, Saha, take the values with a skip count of 10, 30, 40, 50, 60, 70, 80, 90, and 100 are the Avargiya Vyanjanas. So this is his number system. So again, the same example of one syllable sound gu. Here is g value which is 3 and u value which is 10 power 4. So gu in itself means 3 into 10 power 4, which is 30,000. Right? So that's the power of the Aryabhatta number system, that in a very small notation, it's able to capture a huge value. For example, he gives Qgr in his Aryabhatiyam work. Right? So he says, Yugaravi Bhagana Kyugr Shashi Chayagi Gungishu Bundush Kriprak Shani Dung Vigvaguru Krityu Bhakuja Bhadlajn Kr Brug Buddha Sauraha. It's very, very tough to pronounce these numbers, right? Especially in the Arya meter. So hence, Arya, and hence in our Gurukulam, Aryabhatiya is a very favorite class for children because it very, very tough to pronounce. So they take this as a challenge, and then they start chanting very quickly. But however, so Kyugr here, right, the few rules are quite different in Aryabhatiya number system. First, when you see ig plus r, right, and then you've got e plus u, but ik does not have any vowel. So whatever vowel that follows it, plus ik plus e plus u, so ik will also take us place value. That's how Aryabhatiya number system works. So ig is ka ka gha, right? So we know ka ka gha, ka ka gha gha, gha is 4 and r is 10 power 6, right? When it comes to ka, it is 2 and u, so e means 30. So q is 32 into 10 power 4. So g is 4 into 10 power 6, e is 30 into 10 power 4, k and plus u is 2 into 10 power 4. So if you put together, it gives you this number, which is 4,43,20,000. This is the number of revolutions made by sun in a Mahayuga. This is the apparent number of revolutions. This is basically number of years in a Mahayuga. 4.32 million years. Chayagiing Nyushuchlu. That is the next word that Aryabhatta gives. Right? We have ich plus a, e is e plus a, gi is g plus e, yi is e plus e, ng is ng plus u, shu is ish plus u, chlu, which is ill plus r and ich plus r. So if you convert that again using this table and values, you'll see that you'll get a big number, right? This is 5,77,53,336, right? So or 577,000. No, 577,553,000. No, 57,753,336. So this is the number of solar revolutions in a Mahayuga. Lunar revolutions in a Mahayuga. So this is all he uses. So he uses this to bring in big numbers into his Aryabhatian number system. We'll be again using this in trigonometrical context. So I'm just introducing this number system to you. Very ingenious number system, right? Primary vowels, they represent powers of 10 in the even numbers. Then the long vowels, they take the same positional value as the short ones. Consonants are divided into avarga and avarga. And the special rule is that consonant consonants will take the next vowel for its place value holder. And it's easy to write, but very, very tough to pronounce. It qualifies also as a centesimal number system because of the even powers of 10. That is the Aryabhatian number system. Was that okay for everyone? Yes, Anandji.
Madhya, so one question. Um,
Ah.
so if you take the ratio of those two, does it approximate to a high degree of accuracy the ratio of lunar year to solar month? I mean, sorry, solar year to a lunar month, because that is what those two numbers should represent, right? In one Mahayuga, you have how many revolutions of
Not at all.
sun?
Not
So
at all, Ji. A revolution of a moon does not qualify as a lunar year, Ji. A revolution
no,
of a
no
moon is
lunar month. I said a month, because
lunar
you don't
months.
have 12 months in a year, right? You have slightly more. So I was wondering if that ratio is actually accurate compared with the modern value.
Again, it won't exactly be. Again, revolutions of a lunar cycle won't be lunar months also, G, because lunar months are calculated in relative position. It has to be in 27.33 days, a lunar revolution will get over. But the average duration of a lunar month is 29.5 days. Why? Because we want the same tithi to come. We want the same angular separation between the sun and the moon. So what happens is it takes an extra time. It finishes the revolution, then it takes a little more time for the moon to come with the same angular. So let's say we are going around in an orbit. It's a slight digression to what this class is. However, just to explain
Oh,
this.
Mother, then we can follow it offline. I don't want to affect everybody.
Sure, Ji. So lunar revolutions does not mean a lunar month as well, Ji, to summarize. So it has to come with the same angular separation. So in the orbit, we would have moved further around, right, in our orbit across, along the orbit of the Earth. But the moon, it will complete a 360-degree. But for it to come to the same tithi of Amavasya, it has to go a little more and then come. So a lunar month is 29.5 days on an average. It can increase, decrease. A lunar year is basically 12 lunar months put together, and this will have Adhikamasa and all that reconciliation. It's a very elaborate system, whereas the lunar revolutions does not calculate the lunar months as well.
Okay, so basically summary is that you're saying these two of those two numbers don't have anything to physical reality, at least like nothing.
They have a lot to do with physical reality to help us do the true positioning of the moon and sun. These two numbers help us. So we know that this is the fraction of the.
Yeah.
So we should count the fractional.
Sorry, go
Please
ahead.
tell me.
Yeah,
So
if it has something to do with physical reality, then we should define exactly what the ratio means and be able to compare it with the latest data, right?
We have done that. All my PhD, we have been doing that. A lot of data is out there, G. We are doing. Yeah.
Okay. Yeah. Thank you.
Yeah. It has a lot of physical value to it. For that, we should technically define a yuga. A yuga is when all planetary alignments happen together. Then, these are basically, why do we take large revolutionary periods? There are large fractions that we work on. So, let us say a moon is in a particular place right now. We say what fraction of a revolution is over. So, these many number of conjunctions that would get, so it works like that. It's a ratio. We will come to it in a sort of a astronomical class or later as well. So this Bhuta Sankhya number system, as I said, preceded both of these, the number systems. And the Bhuta Sankhya number system, as the name itself suggests, it means Bhuta plus Sankhya. That is, objects having a numerical association with them. So this is also called as the object numerical number system. So the numbers that are associated with the beings. Simply put, when I say Veda, you will think of the number. What would the number? 4, right? So Veda would mean 4. When I say eyes, you might think of the number.
2.
Yeah, 2. Not many of us have the third eye open already. So 2, what we would naturally think. When I say fingers, we will think of
5.
5.
Okay, 10 in the Indian tradition. So 2 hands put together is 10. When I say knees, 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 you think of 2, right? 2 knees. So, and when you think of Chandra, there is only one moon for Earth, right? So you would think of one. So, like that, a very common word would be taken and a numerical association, especially some Puranic associations are also there. So, parts of the bodies are used. Then, physical things such as earth, moon, mountain, fire, right? If I say mountain, what number might come to your mind?
Sahasra.
Oh, no Tirupati. If when I say the number, mount, when I say the word mountain, 7, right? There are
Saptagiri.
Saptagiri, yeah, Saptagiri. So Giri is Sapta in the Indian tradition. Though Elugundalavada, you see definitely Saptagiri, but Puranic views there were 7 important mountains, including Meru, Vindhyas, and so on. So there are 7 in the Puranas as the main mountains, mountain deities. Agni. When we say Agni, what might it be?
5.
Treta Agni. In the previous class, we saw of the Treta Agnis, right? Garhapatya, Ahamaniyan, Dakshinagni. Any Agni Hotri would have to keep up these 3 Agnis, right? Garhapatya, Ahamaniyan, Dakshinagni. So, like that, Agni means 3. Directions means sometimes 8, sometimes 10. Intercardinal directions 4, cardinal directions 4, and the top and bottom. So many places directions mean 10. Elephant, Ashtadik Gajas are there. 8 elephants are there in the 8 as the 8 directional palakas. So horses, when we say Ashwinaha, they mean
7.
7. Snake is also 8 because in the same Ashtadik there are 8 elephants, there are 8 snakes as well. Shiva or Rudra means 11 because there are 11 forms of Rudra. Similarly, Vishnu, Indra. Vishnu has 10 avatars, so 10. Indra, Indra would mean 11 and a few things like that. We'll see. Such as then things like seasons, Ritu is Shadritu, and month is there are 12 months. When I say days, there are on an average 30 days and so on. Other bhutas are there. So, for example, 0 is Kam or Akasha, space. Anything, all synonyms of space will mean 0. For 1, all synonyms of Bhumi, Ku, Prithvi, all this would mean 1. Rupa, form, is 1. Chandra, Ratripa, Indu, all synonyms of Chandra are all 1. For 2, Netra, Bahu, Karana, Janu, which is the eyes, hands, ears, right? Janu's knees, right? And they are all 2. The Ashwini Kumaras are twins, 2. Ashvi is 2. So 3, Agni, Hutashana, 1 he. So these are all synonyms of fire. These are all 3. Rama, similarly, there's Balarama, then there is Parashurama, and then Saketa Rama, Ayodhya Rama, that is, right? So totally 3. So 3 Ramas are there very famously in our Puranas. So 3. Gunas, there are 3 gunas. So guna will mean 3. Then Vedas means 4. There are 4 samudras on the 4 directions of a land. Abdhi, Varidhi, Arnava, all synonyms of ocean will be 4. Ishu, Shara, Bana. The Manmatha has 5 banas to attack our 5 indriyas. Okay. So there is a 5. And Ritu and Rasa. Ritus, 6 seasons are there. Rasa, Shad Rasas are there in Ayurveda. You might say Navarasa, but we will see that there will be internal consistency in some mathematical texts. So sometimes Rasa will be in 6. Parvataha, Agni, Parvata, Aga, Achala, Giri, Kshmadara, all these are synonyms of mountain, and so they are 7. Then Muni or Rishi are Sapta Rishis, so 7. Swara, Sapta Swaras. Then these 7 horses, Ashwa, Turaga, Vajin, Haya, all these synonyms of horses will mean 7. Similarly, synonyms of elephant, Hastin, Gaja, Diggaja, all that are 8. Ashta Vasus are there, Vasu is 8. Naga, Sarpa, Ahihi, all these synonyms of snakes are also 8. In the Nanda dynasty, there are Navanandas, important 9 kings. So Nanda is 9. Randra, 9 holes are there in the body. So synonyms of holes, Chidra, all that is 9. Pankti is a famous meter, which is a 10 syllable meter. So that will mean 10. Rudra is 11. Surya, Arka, Bhanu, Aditya. There are 12 Adityas. So 12. Vishvedeva is 13. 14 is Manu. Tithi is 15. 25 tattvas are there in the Indian Vaisheshika Nyaya systems. Then Nakshatra, Bham, Tara, all that are 27 synonyms. Danta, teeth is 32. Deva, Devata, Vibhuda. Indra also, I said, is 11. I will have to check that. Now I'm doubting. Because day before yesterday, I read somewhere where Indra could mean 30. I'll get back to you on Indra in the next session. So 33 is Deva and Devatas, because even when you study Amara Kosha and so on, there are 33 class of Devas, right? Maruds, Vasus. So all these are 33 in number. Vibhudas, Devatas, all the synonyms of Deva are all 33. For example, Surya Chandra, they will say. So Surya is 12, Chandra is 1. If you have to reverse, it will become 1, 1, 2. So within 1, 2, you shouldn't reverse. So 1 and then 1, 2, you should write. Then Gunashvinav. Guna is 3, Ashvi. Here, Ashwin is the twin nakshatras, Ashwini nakshatra. So 2 and 3. These are all some from the Siddhanta Shiromani. I have taken some examples here to show some numbers used there. Gaja Vasu Dantaha. Danta is 32. So they have made the Samasta Pada, because this is basically Dvandva Samasa. Gaja cha Vasu cha Dantaha cha becomes Gaja Vasu Dantaha. So 8, 8, 32. Reversing it, it will become 3, 2, 8, 8. Rama Rasa Rudraha. Rudraha is 11. Then Rasa is 6. Rama is 3. 1, 1, 6, 3. And what this Bhuta Sankhya allows is great flexibility. If your Chandas is a big Chandas, you can use a big word. If you have a small Chandas, you use a small word. And both can mean the same number. Right? Akasha Guna Netra Chandraha. Akasha is 0. Guna is 3. Netra is 2. Chandra is 1. And if you reverse it, it is 1, 2, 3, 0. Kag Nibahu Bhumayaha is also the same. Ka Agni Bahu Bhumaya. So depending on the chandas that you are going to employ, the kind of fillers that you want to use, you can very beautifully use this number system, both to mean the same. Right? Brihat Samhita, right? In the Varahamira gives in Brihat Samhita, right? Some fantastic work. And Bhattotpala, the astronomer who gave the complete commentary for Brihat Samhita, he notes that the number represented by Varahamira in this number, Kakashta Muni Ramashvinetra Ashta Shararatripaha, is nothing but the number of civil days in a Mahayuga, he says. That is the number of sunrises we may witness in a Mahayuga, he says, as per his calculations. So Kha 0, 0, Ashta 8, Muni 7, Rama 3, Ashvi 2, Netra 2, Ashta is 8 as it is, the number itself. Sometimes you will see that, people, put, for example, 3 Guna. 3 will be 3, Guna will be 3. It will be 33 when they say 3 Guna. So Ashta, then Shara, and Ratripaha is Chandra. So it goes like that. This is a beautiful example given by Madhava. He gives the value of pi correct to 11 decimal places in this beautiful verse. Vibudhanetra gajahi hutashana triguna vedha bhavarana bhavaha navani kharvamite vriti vistare paridhimanamidam jagadarbhudaha. It's in the Rathodhata meter. So Vibudha is 33, Netra is 2, Gaja is 8, Ahihi, right? Ahihi is serpent 8. Then Hutashana is fire 3. Then Hutashana 3 is 3. Guna is again 3. Then Veda is 4. Then we have Bham Tara is 27. Varana again elephant 8. Bahu is 2. So this, he's saying, what is he? He's giving a big number here. What is he saying? What is this pi? It's basically the ratio between the circumference to the diameter, right? So paridhi manam, right? Vritti vistare paridhi manam is this thing he's saying. He is giving two numbers now. He is giving circumference to be this big number in the first half of the verse. Then he says, in the circle, in the vistar with the diameter as navani kharva mithe, in that kind of a circle where the vistara, where the diameter is navani kharma mithe, the circumference will be this. He's saying a big circumference value. Paridhimanam idam, the value that has been given. So you see, this is navani kharva. Nikharva we saw is 10 power 11. Navani kharva means 9 into 10 power 11. So if you take the ratio between this circumference to this diameter, you will get the value of pi. So we didn't work on decimal place values, right? We always use fractions in the Indian mathematical system. The decimal place value came into great prominence going to the digital era because it's not easy to represent this, as a fraction. Indians were very, very good in fractions and working with fractions, bhagajati. That is what they were exceptional in. So we see that the advantage of this system is representing numbers in Sanskrit with the words in Sanskrit. Sanskrit language itself is very rich in vocabulary, right? We have so many words for the same thing, right? And thereby giving great flexibility for the poet to pick out any of this and then use. But however, it demands that the reader has a wide vocabulary so that we can decode this very well. There is a book that I've been working on as part of my research, Malari's text called Parvadbhaya Sadhana, and it's full of data tables and it's full of Bhuta Sankhya. Thankfully, many manuscripts have written the data table also along with the verses. Thereby, we can slightly try to understand, and then what interpretations of the words are there. So this concludes our number representation system. We'll be seeing applications of it, but this is sort of a primary knowledge that we must have about Bharatiya number representations. And we'll enjoy applications of this in the coming lectures in various rupas, various forms. Hope you all enjoyed this session as much as I did. And this everything that Indian mathematicians have done are very, very beautiful, very useful, very unique to the context that they belong to. And the more we study them, the more I find greater pedagogical relevance even now to create beautiful exercises for our children. Thank you all. If there are any questions, we'll see that and we'll. Okay.
Okay.
Excellent session, Madhya.
Yeah, that was
so much.
very, very good. Excellent set of information. Yeah.
Thank you.
Yeah. Okay. Looks like there are no more questions. Then we'll just conclude. Oh, sarve bhavantu sukhinah, sarve santu niramayah, sarve bhadrani pashyantu, ma kaschid dukkha bhag bhavet. Om Shanti Shanti Shanti. Hari Om Shri Gurubhyo Namaha. Hari Om. Thank you all. We will get the slides and we'll post it and some supplementary material to go with it. Thank you. Have a great weekend.
ಧನ್ಯವಾದ.
Dhanyavada, Gurupriya.
Dhanyawada.
Namaste.